Welcome to the second part of this chapter. So in this section, we're going to be talking about physical properties. So a physical property is a characteristic that can be observed without changing the identity of the substance. So this is talking about on the atomic level. So if you're going to talk about physical properties, it can't be anything where the compound, like the actual chemical bonds, atoms, all of that change. Okay, so physical properties just deal with like size and shape of something on the macro level, different things like that. So some examples of physical properties are color. Okay, if you have a color change, that is a chemical property or chemical change, not a physical change. But just the color of something is a physical property. You also have mass, so how much an object weighs. You have the shape of the object, the density, so we're going to go over density in just a little bit, and then also the melting and boiling points. Okay. So density is a measure of how much matter is condensed into a specific volume. So it's kind of a measure of how many atoms are shoved into one specific area. Okay, so density is calculated by taking the mass and dividing it by the volume. So density equals mass divided by volume, or if you shorten it, it is capital D equals M divided by capital V. So if you have 10 centimeters cubed, so that is a volume of ice, and it has a mass of 9.17 grams, what is the density of the ice? Okay, so for this, let me get a pen here. Okay, so for this, you've got your volume here, okay, and this is your mass. All right, so this is where coming in, knowing your units comes into play here. Okay, you know that anything that's cubed, okay, any unit that's cubed, like you've got the centimeters cubed here, that is going to be a volume unit. Okay, and then you know that grams are always mass. All right, so we've got our volume, we've got our mass, and we're solving for density. Okay, so we don't know density, so that is just the capital D equals, okay, and then we've got mass. All right, so mass goes on top here. So we can go ahead and write the 9.17, that's grams. Okay, and then we have our volume, which goes on the bottom. So 10.0, and that's centimeters cubed. Okay, so that's how you set that up. So, if you go ahead and divide this out, so go ahead and pull out your calculators and actually do that. Okay, so you're going to end up with your density equals 0.917. What's up? What else? Can't forget your units. Now this one is a little bit strange because it's a combination unit. Okay, so you don't have anything to cancel out your grams. You don't have anything to cancel out your centimeters cubed. So this one, your units are grams per centimeter cubed. Okay, it's a bit of a strange. Okay, so with the next one here, it will let me advance the slide. There we go. All right, so find the density of a sugar cube where each side is 2 centimeters and the mass is 11.2 grams. All right, so with this one, it tells you that you have a sugar cube. Okay, so when you have a cube, because it's using that terminology of cube, you can go ahead and assume that all the sides have an equal length. And then it actually tells you each side is 2 centimeters long. Okay, So to calculate volume, remember you're going to do length times width times height. Okay? Now because it's a cube, again, length, width, and height are all the same, and this tells us that it is 2 centimeters. So basically it's going to be 2 centimeters times 2 centimeters times 2 centimeters. So you could also write it as V equals parentheses 2 centimeters, okay, and that's cubed. So in order to do this, you're going to cube both the number and the unit. So this ends up being 2 cubed, which is 8, and then centimeters cubed. Okay, and that's our volume. So now we're going to set this up pretty much exactly the way that we did before. Okay, we just had to do one extra step to find our volume. So now we have mass is given in the problem. So we have 11.2 grams. So that's going to go on top here. Okay. And now we can put the volume that we just found on the bottom. So 8 centimeters cubed. So you should still have your calculator out. So go ahead and solve that. So you should have gotten 1.4, and then again it's grams per centimeter cubed. So you're not always going to get grams per centimeter cubed as your units for density. It's always going to be some mass unit over some volume unit. So this could be grams per milliliter, could be grams per liter, could be kilograms per liter, okay? It really just kind of depends on what you're given in the problem. All right. So scientists had to figure out some way of measuring the volume of irregularly shaped objects. So if you have an object that is a perfect sphere, perfect cube, prism, anything like that, you can basically measure the sides and calculate the volume. But if you have like a chunk of metal, it's oftentimes not going to be in some kind of perfect shape like that. So it's a very odd shape. And they had to come up with some way to actually measure the volume of these objects. So first thing you want to do when you're doing this is you want to fill a beaker with enough water to cover the object. Okay, you don't want to fill the beaker all the way up because then it's going to overflow during this. Alright, so you just want enough water that it's going to cover the object. Okay, so this is our initial volume here. This is a bit of a strange beaker because it's measured in thirds. Okay, third of a 10. Yeah, it's weird. But, alright, so first step is you want to measure your initial volume. Okay, and then you're going to record it. So what do you think this volume is? So this line, it's a little weird looking, but this line is actually what you're going to be trying to measure. Okay, and then because this is measured a third of every 10, okay, this would be roughly 13.3 milliliters. Okay, granted this beaker does not actually have any units marked on it, but we can go ahead and assume, at least right now, that it's in milliliters. Alright. So your next step is you want to place the object in the water. Now, I think it's funny that your textbook has this, and it's talking about measuring the volume of oddly shaped objects, and it puts a cube in the beaker. But anyway, okay? So, you've got your object submerged in the water, and again, you need to double check to make sure that it is fully submerged in the water. Okay, if it's not, you have to take the object out and add some more water to the beaker. All right, and now you can record the final volume. So what do you think this one is? I would say it's about 22.5. So it's not all the way up to this mark here, which would have put it at 23.3. So I was going to estimate about 22.5 milliliters. So the next thing you want to do, okay, you've got the data that you need. So the only thing that changed between your initial volume and your final volume was the addition of the object. Okay, so it means that the volume's object is equal to the final volume subtracting out the initial volume. Okay, because in that, basically your final volume is the volume of the object plus the volume of the water. Okay, and the volume in the initial beaker is just the volume of the water. So by subtracting out your initial volume, all you're getting is the volume of the object. Okay, so it's the volume of the object equals the volume of the final beaker minus the volume of the initial beaker. Okay, so you have 22.5 minus 13.3. Okay, so what'd you get? So this object is roughly 9.2 milliliters in volume. Okay? All right. So physical properties can actually help identify a substance. When you have a specific combination of physical properties, it's actually really unique to each individual compound. Okay? So each compound or element has its own set of unique set of physical properties. Okay, so oftentimes you will have to measure multiple different physical properties in order to get complete confidence in your identification of the substance. But sometimes you can do it with like just a handful of physical properties. This video is here to remind me to tell you about the Archimedes video. Okay, this whole principle of basically measuring the volume of an object by placing it in water and then measuring it's called the displacement of the water, so how high the water level rises. Okay, that was actually discovered by Archimedes, and it's kind of an interesting story. But I'll leave that for the other video that I've posted about that. Alright, so then talking again about density. So which is denser, a brick or a sponge? So remember, this question is asking how closely packed are the atoms in both of these objects. Okay, so you've got a brick, which is very solid. You can't squish it. Okay, so it's got a lot of atoms packed in really tightly there. And then you've got a sponge. Okay, so a sponge, yeah, you know, it's not all that packed in there. You can actually squeeze it pretty decently. Okay, you're going to decrease the size of the sponge quite a bit. So in this case, a brick would be much denser than a sponge, even if they're the same size. Okay, so you can also think about it as if you put both of these on the surface of a lake, what would happen? The brick would sink, and that's because it's denser than water. But the sponge would most likely float simply because it's less dense than water. Alright, so what do you think about this one? Which one's denser? A solid is almost always, well, a solid will always be denser than a gas and almost always be denser than the liquid form of the same compound. Okay, so here you have gaseous carbon dioxide and you have dry ice, which is solid carbon dioxide. So this dry ice will be much denser than the carbon dioxide. And finally, this is one of those weird cases where the solid is actually less dense than the liquid. Water is one of very few compounds that does this. Okay, usually it's the solid is the densest, gas is the least dense, and then the liquid is somewhere in between. But that is actually why ice floats in water. It's because it's less dense than the water. Alright, so that is it for this section.